Okay, cool. I think the question we just had was a good segue into this. So I'm Stephan. I'm the overall TL for XLA CPU GPU. And I will take you through like a 5-minute whirlwind through what we have planned for this year. And I guess no surprise, if I would summarize this in like one sentence, what are we doing? It's like improving performance for transformer-like models on single GPUs, multi-GPUs, right? So that's the broad area we're looking into. So let me unpack this a bit. I've structured this in like 3 major work areas. So the first one being horizontal scaling. So that's essentially multi-GPU. And what we've done there so far this year is we completed our support for asynchronous collectives. So we initially only had like all gather, I think, and now we have all of them. And we also have like early support for scheduling and latency hiding. And that's also where we will be looking for the next 2 quarters. Like improving the latency hiding scheduler. So we have ideas where to take this, like doing cost models or doing this profile-based. So that's a big stream of work. And the other stream is tuning collectives. And that can take like many different ways. So it can be just nickel tuning, or it could be writing bespoke collectives. It can be decomposing collectives. It can be things like fusing into collectives. Can be all kinds of ideas we have, and we're just exploring what gives us good performance there. And as you can see, the last box is empty, and that doesn't mean that in Q4 we won't do anything in horizontal scaling. It's more like we expect that we discover more issues we have to look into as we go. So it's like the let's see where we are in Q4. It's also a good area to give feedback, right? If you have ideas of where we should be looking then. So that's horizontal scaling. The other thing is performance. So what are we doing there? So what we've done up until now, fairly successful, also is tuning our existing code generation stack. So that was a lot about tuning layout assignments, tuning fusion heuristics. We got like 10-15% on some larger models just by doing this work, like readapting to the change of structure that models are showing. Another big work stream was landing FP8 support. So that's also available, and that's still ongoing. So that's up until now. Looking into the next 2 quarters, what we're going to be doing, we're looking into what's called Triton-based matmul here. So that's essentially like traditionally XLA had the strategy to just use libraries. And we're just opening this up a bit, and we're also looking into like the Triton compiler backend to give us some matrix multiplies. We've started work in that area. We also are landing CUDA graphs, so that's for reducing latencies of kernel launches we have. So it's a very small investment for a big effort. Just if you have sequences of kernels, launching them in one. And then there's this box there, improving tiling search. So as we're moving away from libraries, but you also have like code generation for matmuls ourselves, we often have to regain essentially what libraries give us, right? So libraries are pre-tuned. We now have to tune our code generation ourselves. So we're investing there in doing like search-based ways of doing tunings and tile size selection. And looking further in Q4, what I've called advanced fusions here. So that's like looking into things like soft maxes, multi-headed attentions, but ones that are a bit more bespoke, right? So if it's a standard multi-headed attention, you could just write a kernel for it. But if it becomes a bit more specific or has been altered in slight ways, right, it would be nicer to have code generation. So that's an area where we think we'll be investing in Q4 more. And then lastly, extensibility. So what we've already done is on the GPU side, we've rolled out the XLA runtime. And that gave like many features, but on the extensibility side, 2 things that came was a better FFI. So it's much easier to do custom calls. You have a richer interface there. I think that's helpful. And on the other side, we also added support for asynchronous values, right? So you can think of like you pass a future in, you get a future out, and that makes it a lot easier to embed XLA into larger contexts. What's happening in Q2 and Q3? So we will bring the runtime also to the CPU side, so that we have feature parity. That's coming. And the other big change that we're rolling out is like a rewrite of the code generation on CPU. So we've rewritten this based on top of MLIR. And this is under extensibility. It gives you more performance, right? It's faster. Otherwise, everything is about performance. But the important key thing is also it's very extensible, tunable. So it's a very different way to do code generation. And then lastly, Q4, better Triton embedding in XLA. So what that means is, right, it's not Triton specific in that sense. Like people write kernels themselves, they write bespoke fusions themselves, and we just want to make it easier for them to get this through XLA and kind of land it in production, serve it, like this entire kind of usability aspect of how can I extend XLA with handwritten fusions. So that was my 5-minute whirlwind. I think that's like the agenda for the year. I think we will have sessions about feedback on this. It's highly appreciated. With that, it's over to Matt.
Yeah, hi, I'm Matt. I'm the technical lead on the OpenXLA compiler. For those of you that are Erie users, one mental model for this is this is in a sense the evolution and the continuation of the Erie work. And as we've been talking about performance, I'm not going to do a jumping on stage, but that clearly is the theme of everything we're doing. And the different slices of that are both in terms of exploitation of the hardware on the single, kind of in a single node view, and then the multi-node view, and you'll see that kind of theme run through here. First thing I'll just talk about is changes that are almost ready to go. Some of them are hidden by flags, but the team has been really heads down working to exploit Tensor Core in ways that we hadn't before. And you're going to have a terrific talk from Manish later today. Don't miss that lightning talk where he'll talk to you about the evolution of where we started and where we ended up. And that's going to continue to go on. We've invested heavily in bespoke or built-in code gen into Erie, and we consider that an essential element of success in what we're doing. Now let's talk about the things that are coming in the different quarters. And of course, modulo things sometimes are done and then they're done. And so I want to be these are predictions and what we're shooting for. So we're going to hear a lot more about PJRT today, and also our PJRT integration is a hot effort that's getting more and more attention for the coordination piece and that linkage between the HLO layer and below. And then also the SPIMD. Today there really hasn't been till now a SPIMD mode within Erie or OpenXLA compiler so that you could actually do multi-node training, for instance, and that's coming online and that's getting a lot of attention now. To be fully JAX compliant in Q3 is another thing going on. If you guys see Jacques, I'm sure he'd be happy to tell you the status of that. We're getting closer and closer to having no regressions on that. And as well as I mentioned before, the partitioning element of the SPIMD and its integration with JAX appears in Q3. That's how we'll know that we're actually doing it. And then more of those performance improvements I mentioned specifically and how we process batch matmuls, split matmuls that have relatively large K. Again, it's going to be covered in Manish's talk. Unaligned matmuls, all different things, all to improve our built-in code generation. Convolution performance will improve as we leverage our matmul work with implicit gem, and we will link those two together, and that we expect to come online, especially with some support in Q3. And also, as much as I'm excited about our bespoke code generation, we also recognize the important role that libraries have to play, especially for day zero support and that kind of thing. So we are bolstering right now our ability to link libraries in different ways in different modes and to have realizable performance down that route also. As we head into Q4, Hopper support becomes a much bigger Hopper support becomes something that we're going to be increasingly focused on. We're already doing some preliminary experiments there. One thing I hadn't talked about up to this point is the runtime. We had a question earlier about the footprint of Erie and so on. And you'll notice that there isn't a whole lot of new runtime capability in there. We feel pretty good about the state of the runtime in terms of capability, but we recognize there's some improvements we can make in terms of how the asynchronicity of our current CUDA HAL is not on par where we are on our Vulkan and other backends. And that work is going to roll on this year also. Tuning right now, we really is kind of either done is done by you, and that will still be a semi-automatic feature, and that we'll still believe it's something that the user will influence, but we're going to improve the way that we can have that be automated and exposed and simplified. And that's still being developed, but obviously that's table stakes to participate here. And last but not least, not necessarily in Q4, but through more deep dive workload analyses, we discover more fusion opportunities, softmax we mentioned before, and that work is ongoing to improve Erie's whole program optimizations that will improve those also. I hope that will at least whet your appetite for some of this that we're going to dive into in the lightning talks. But for now, I will pass this, I believe, to Eugene. No, down, space, there we go.
Hi, everyone. Thank you, Matt. Well, let's talk a bit about StableHLO. And here on the slide, apologies if the font is too small. Try to fit a lot of information here. I split the tentative plans for 2023 into 3 buckets, going from top to bottom. And by the way, when I'm saying tentative plans, what I mean here is that this is something that we on the Google side are planning to invest in, but we would love to make this roadmap your roadmap. So if you have ideas, what makes sense more, or if you have something that you would like to contribute to, please let us know. We're going to have a StableHLO roadmap workshop shortly, in like half an hour. So do let us know. And overall, the spirit of the OpenXLA project is to do things together. So this is not like, well, Google is going to define this roadmap and that's it. Not at all. So please talk to us. Now back to this slide. As I said, we kind of have we split the year into 3 parts. The first part at the top, we have the StableHLO 0.9 release. That's already happened. We announced that at the end of Q1, so beginning of March, presented that at GTC as well. And a notable thing is about this release is that it enabled integration into other systems, because this is when StableHLO really started providing compatibility guarantees. Currently, we have 6 months backward and 1 month forward compatibility that allowed us to make this available in saved model. So saved model part of TF. This is something that is used extensively here at Google for production purposes. So that was important for us to integrate. There's a hyperlink there. If you click it, you'll see like a documentation of specific way how this is plugged into saved model. I will not spend more time on this now. Now, in the next 2 quarters, so Q2 and Q3, we want to lay the groundwork for the StableHLO 1.0 release. We want to clean up our front-end contract so that ideally all the programs that our front-ends produce, StableHLO programs, they consist of StableHLO ops. Currently, it's a bit of a mix of some unregistered attributes. There's some like weird ops. We want to clean this up so that everything is documented. We have a reference implementation for all this stuff so that both front ends and back ends can agree on the semantics, which is written down somewhere and audited, reviewed by the community, you all. And finally, we want to have really good documentation for that stuff. And then, as I said, this will lay the groundwork for the 1.0 release. There are still some work streams which are called out in the bottom third, like conformance suite, specification compliance, which will be ongoing. We don't expect them to stop when 1.0 will be released. Not at all. They will go all the way into 24, 25. But for 1.0, this is the critical subset of functionality that we identified as interesting. I guess this is it on my side. Do let us know if there's something more that you need, in addition to like dynamism, quantization, sparsity, distribution, which were called out earlier today. And we'll be happy to accommodate. We'll be happy to work with you all together on that. At this point, I'll hand this off to the next presenter. I think that's going to be Aman. Oh, Puneith. All right. Thank you all.
Cool. Hi, everyone. It's great to be here and welcome to the summit. My name is Puneith and I lead the OpenXLA infrastructure at Google. As the term tells you, I mean, our focus is infrastructure around OpenXLA. And really 3 things, 3 buckets of our work. One is what we call the SEM dev infrastructure, which is all things around your overall GitHub contributions, contributions from NVIDIA and Apple and other companies, and making sure that that experience is excellent. Number 2 is benchmarking and metrics, and I'll go over a little bit details in a minute. That's very critical because as you are doing compiler development, it's very important to detect hotspots, where the performance regressions are happening. And number 3 is testing. Compiler testing is not your classic imperative testing. You can't really handcraft tests, and so we have fuzzing as a mechanism to do testing. To that end, some of the highlights in 2022 and Q1 2023, we launched the OpenXLA standalone repo. You heard a lot about our overall mission, a lot of excitement around that. We also recently enabled 3P contributions for OpenXLA, so you can now directly go to the OpenXLA and send your pull requests, and they will get basically merged. You don't have to go to the TF-XLA. The third is for us, because we are working towards a community, and so the adoption of how well we are doing in the communities is very critical, and so we also kicked off that work stream for the adoption tracking, like how well we are responding to the pull requests, what's our SLO, and how well we are doing on the SLO SLA compliance and the turnaround. Quickly for Q2 through Q4, a few things which are on our plate. We actually, JAX already depends on OpenXLA, so the work in Q2 for that was pretty much enabled. But that's really our commitment to how we want other pieces of frameworks, JAX and PyTorch, to be reliant on OpenXLA. And so that's very important for us, and we enabled that in Q1. Fuzz testing, as I mentioned, we don't have fuzzing in the open source today, and we believe that if you really want to accelerate the testing of compilers, detect crashes, there's a lot of fusion happening in compilers, and so how do you detect softmax fusion crashes automatically? And that's fuzzing for you, and really generating regression suites when external pull requests are kicked off, then making sure that that goes through this fuzzing infrastructure, and the detection happens much more sooner. The third is the competitive benchmarking, ERXLA. Like I said, benchmarking is extremely critical. And so what we plan to do is to create an open source benchmarking infrastructure, which is going to be running on the cloud, GCP. We recently just did some POCs around BigQuery and Looker Studio, so that all that code and infrastructure is available out in the open for you to take a look at. Then finally for Q2, like shared CI across GitHub repo, making sure that we have coverage across multiple platforms, x86, ARM, RISC, and across multiple operating systems, Linux, Windows, and so on. And then also GitHub Actions and runners. ED already does that today. How to extend that into the OpenXLA domain overall. Increasing the TF JAX test coverage, that's ongoing. Then in Q3, again, in the same spirit of JAX enablement, we want to make sure that PyTorch actually uses OpenXLA, again, to prove our commitment towards OpenXLA as far as the infrastructure goes. We then want to make sure that we have benchmarks which are StableHLO-driven benchmarks. As you know, that frameworks can introduce noise in the benchmark, and so you will hear a lot about StableHLO today, and Eugene was mentioning about the roadmaps, and so we really want to make sure that we are aligned with that roadmap overall. And then OSS benchmark dashboards is what I was referring to previously, which is looking at things like Looker Studio, BigQuery, using that as the storage, analytics, and reporting platform. And then finally, Q4, this one is a little bit not super crystal clear, but we think that we really want to also focus on the compilation time benchmarks. Again, with frameworks, there can be noise introduced or passes, which happen in TensorFlow. And so we really want to make sure that we have HLO level benchmarks, or stable HLO level benchmarks which can give stability and reliability with regards to numbers. And then the final two are we want to make sure that we are delivering a single infrastructure across multiple backends. And that's consistent metrics across CPUs and GPUs, making sure that the telemetry, the inference and the reporting of all those numbers is done once, and that we don't have multiple infrastructure across multiple backends. And then finally, again, for the fuzzing, we want to rely on production grade machine learning models out there and use them as our guiding corpus to create these fuzzing programs, which as compiler development is happening, that we can validate and confirm that there's no regression happening on our code change. That's all. Definitely encourage. We're going to have an open source benchmark roundtable later in the afternoon. So yeah, definitely encourage you to attend and learn more. Thank you.
Yes.
Okay. Can you folks hear me fine? All right. I'm going to continue speaking. There's no feedback. So yeah, thank you and good morning, everyone. My name is Aman Verma, and I'm a product manager here at Google for the ML runtimes and APIs. I'm really excited to be here to introduce PJRT to many of you. We have a deep dive session right after this, where we'll be happy to take all your questions. So let's get into it. Next. Okay, so as we know, infrastructure fragmentation in machine learning across frameworks, compilers, and runtimes, makes developing new hardware and toolchains difficult. This inhibits the industry's ability to productionize ML-driven advancements with velocity and at scale. Today, the ML workload execution has to support a combinatorial matrix of hardware, frameworks, and workflows, mostly through tight vertical integrations. Examples of such vertical integrations include specific kernels for TPU versus GPU, specific toolchains to train and serve in TensorFlow versus PyTorch. Now, these bespoke 1:1 integrations are perfectly valid solutions, but they promote lock-in, inhibit innovation, and are expensive to maintain, right? So this problem of a fragmented software stack is compounded over time as different computing hardware needs to be supported. Next. And we know that a variety of ML hardware exists today, and the diversity is expected to increase in the future. That is, ML users have options today on hardware, and they want to exercise them seamlessly. For example, train a large language model on TPUs in the cloud, then batch infer them on on-premises GPU or CPUs, and then distill, quantize, and finally serve them on mobile processors. Next. So to simplify this growing complexity of ML workload execution across hardware and frameworks, we are excited to introduce PJRT and open source it as part of this recently generally available OpenXLA ecosystem. Our vision here is to solve this challenge of portability of ML workloads across hardware by simplifying the integration of the hardware into the infrastructure of framework, compiler, and runtime. Next. So what is PJRT and what does this give you, right? PJRT provides a hardware and framework independent interface for compilers and runtime. Next. It simplifies the integration of the hardware to the infrastructure, accelerating the framework coverage for the hardware, and thus the hardware targetability for the workload execution. Next. So if you are developing an ML hardware accelerator, compiler, or runtime targeting any hardware, or even just converging siloed tool chains to solve infrastructure fragmentation, PJRT can minimize the bespoke hardware and framework integration, providing greater coverage and improving time to market at a lower development cost. Next. So how does this all work together? The workflow to provide workload portability with seamless execution with PJRT is as follows. The hardware-specific compiler and runtime provider will implement the PJRT API, package it as a plugin containing the compiler and runtime hooks, and register it with the frameworks. This implementation can be opaque to the frameworks. Then the frameworks will discover and load one or multiple PJRT plugins as dynamic libraries, targeting the hardware on which to execute the workload. And that's it. Now we can just execute the workload from the framework onto the target hardware. The PJRT API will be backwards compatible. The plugin would not need to change often and would be able to do version checking for features. Additionally, the PJRT plugin can provide custom kernels and APIs as well. And the frameworks can provide their own APIs for these custom kernels. For example, TensorFlow provides the pluggable kernel API. Again, we'll get into more details on this in our deep dive session. Next. So, as a foundational pillar of the OpenXLA project, PJRT is well integrated with projects within the OpenXLA ecosystem, including StableHLO and the OpenXLA compilers. Now note that PJRT is the primary interface for TensorFlow and JAX and is fully supported for PyTorch through PyTorch XLA. It is well integrated with the OpenXLA compilers to execute the workloads on TPU, GPU, and CPU. It is also the default runtime execution path for most of Google's internal production workloads. Next. However, apart from being hardware and framework independent, PJRT is also not coupled with a specific compiler. With framework integration through StableHLO, PJRT can be used outside of the OpenXLA ecosystem, including other proprietary compilers. The open source availability and the toolchain independent architecture allows it to be leveraged by any hardware, framework, or compiler with extensibility for unique features. And again, we can discuss some of this in later on in the deep dive. Next. So beyond Google, PJRT has already been adopted by industry leaders through close collaboration. For example, Intel is leveraging PJRT in the Intel extensions to provide the Intel GPU backend for TensorFlow and JAX, and very recently PyTorch as well. Intel's documentation has an example of executing a JAX program on an Intel GPU that demonstrates how this greatly simplifies the framework and hardware integration. Additionally, we're also working with another technology leader for them to leverage PJRT to provide the backend targeting their proprietary processor for JAX. And more details are going to be available soon. Next. So if you develop ML frameworks, compilers, runtimes, or are just interested in improving the portability of workloads across hardware, we want your feedback. The PJRT source code is available on GitHub. We encourage you to contribute code, design ideas, and feature suggestions. We also invite you to join the OpenXLA mailing list to stay updated with the latest announcements around product and community. We'll go deeper into the details in our PJRT session in a few minutes. So if you have any questions, feature suggestions, ideas for collaboration, let's please head over to the right room. And that's it. Thank you.